Hello, I'm Sierra Stockwell. I'm the president of MASA-Dearborn, also known as Team 119. Today we'll be presenting our rocket, Boosted Bear, the Next Generation. Boosted Bear, the Next Generation is MASA-Dearborn's fifth rocket designed for Spaceport America Cup. This year, our rocket has a few new goals: to gather data on the denaturing of DNA and enzymes during flight, to utilize an Airbrake system to get as close as possible to our target apogee, and to successfully reduce the number of parachutes needed in our rocket with the reefing system. Here's our launch vehicle summary. Our rocket length is 11 feet 4 inches. Our weight with the motor is 56.3 pounds, and our weight without is 37.6 pounds. Our motor choice is the Cicerone M795, and our first recovery system utilizes the MissileWorks RRC2 altimeters for booster parachute deployment, and our second recovery system utilizes MissileWorks RRC3 Plus altimeters for dart parachute deployment and separation. Here you can see our mass distribution by percentage and weight, if you're interested. And this is our concept of operations. As you can see, we fly in a boosted dart configuration. So we start off with the booster and the sustainer in one piece at launch, and then our motor burns out at 12.7 seconds at a 7,000 foot altitude, and then our booster separates at 14 seconds at 8,000 feet to go on to its own apogee at 23 seconds and 9,200 feet. Our booster main parachute then deploys at 72 seconds and 1,500 feet, and then our booster lands in 85 seconds. Our dart goes on to our target apogee, but before that happens, our Airbrakes deploy at 14 seconds and 8,068.2 feet. Then our dart reaches apogee at 22 seconds and 10,100 feet. Soon after, our reefed parachute deploys at 29 seconds and 9,400 feet, at this point acting as a drogue parachute. Then in 68 seconds at 1,500 feet, our reef is cut to expose the main parachute formation of our reefed parachute. And then our dart lands at 76 seconds. And now for airframe.
My name is Sarah Dormal, and I will be presenting the general airframe section. The general airframe consists of the dart and the booster with the flight package joining the two. Several bulkheads are located throughout the rocket to protect systems when the rocket separates or when parachutes deploy. All of the joints between the body tubes will be connected by 1 cal of commercial off-the-shelf fiberglass couplers. Due to complications with COVID, the team has been unable to enter our facilities, so we elected to buy body tubes and cut out any holes or slots in-house. The goal for this rocket was to move to airfoil fins, but manufacturing proved to be too complex for this year, so the team elected to replicate past designs for the static fins. The static fins are a trapezoidal shape made from carbon fiber pre-preg aluminum honeycomb sandwich composite and a 3D printed edge. These will be mounted through the body tube onto the motor tube. Next is the camera shrouds.
Hi, I am Andrzej Sterko, and I will talk about camera shrouds. The camera shroud's purpose is to protect the cameras and maintain the aerodynamic properties of the general airframe. The shrouds will be made from studied research and developed carbon fiber and resin composite, similarly to the sandwich composite that is being used for the static fins, but using the vacuum bagging method. The team has decided to use this method and materials because carbon fiber is light and strong, and vacuum bagging is an efficient way to attain designed shape for the camera shrouds.
My name is Barnabas Toth, and now I will talk about the deployable fins. The deployable fins are housed at the bottom of the flight package and are stored in the rocket until separation. The fins provide flight stability during the second stage. The system's bottom bulkhead provides a stiff mounting platform for the threaded rods, which hold the flight package together. The fins open downward for reliability. The team added a set of T-bars to mitigate previous rigidity issues with a downward opening configuration. The T-bars are going to be milled out of 2024 aluminum, while the bulkheads and the fins are going to be CNC'd out of 6061 aluminum to cut costs.
I'm Ali Sablini, and I'm going to be talking about the Airbrakes. This year, the team added Airbrakes to the rocket. The Airbrakes extend or contract to slow down the rocket and place the rocket closer to our target apogee. This system is housed in the flight package and located in the center of the rocket. We plan to manufacture both the plates and the blades on the CNC mill, as tolerances are an important factor in ensuring the brakes deploy correctly. To reduce strain on the air brakes, a fiberglass brace was added around them, and a bulkhead was fixed underneath. Because this is the team's first attempt at making air brakes, we made the decision to design the mechanism as simply as possible. Due to pandemic conditions, the team decided to cut costs and manufacturing time by reducing the scope of the system. Using a motor with a D-shaft, we spin a disc that is connected to the blades to control their movement.
I'm Maribeth Moan, and I'll be talking about the electronics mount for the Airbrakes. The airbrake controller mount that sits around the motor was designed to integrate easily onto the threaded rods holding the flight package together. The design has 3 tubes to accomplish this, and 3 walls between them to hold the electronic components of the airbrake controller and battery supply. The mount is to be manufactured using 3D printing because of the complex shape of the part. Next, the payload subteam will discuss the experiment.
Hi, my name is Devin Neimer. I'm the payload mechanical lead, and Logan Kilby will be covering the general payload system.
The payload is located in the uppermost section of the rocket. It houses the flight data electronics and contains our biological experiment. The experiment is located near the bottom with the electronics above it, which are composed of the Telegps, 3-space, Raspberry Pi boards, and cameras, which are all powered by a battery unit near the top. Our payload system was designed to integrate into the airframe with a few key features. On the bottom mounting plate, we included a notch that aligns with the rectangular piece bolted to the airframe bulkhead. This feature allows us for simpler alignment of the cameras through their designated airframe holes.
We've already printed prototypes of our PET-G mounts at home with our at-home printers. Our plan is to mill the camera mount and use the CNC for our fabrication of the frame and its alignment jigs. All this will be completed assuming we are granted access to our manufacturing lab on campus in the expected amount of time. The lack of resources this year has challenged us to keep spending low while incorporating the necessary components for our rocket to perform. For instance, we utilize 3D printing far more often than in prior years. The filament choice was therefore a very integral part of our build. With that in mind, we chose PET-G for its ease of printing and its superior glass transition temperature when compared to its commonly used counterpart, PLA.
Hi, I'm Shivani, and I will be talking about the DNA experiment. So the experiment is fairly simple. We are testing to see if double-stranded DNA will denature, hybridize, or mutate upon the various flight conditions the rocket will undergo. We will use a spectrophotometer for data collection. The desired wavelength of the device we want to see is somewhere around 260 nanometers. This is when the duplex DNA typically begins to denature. Strands of duplex DNA will be placed in a small 4 milliliter cuvette completely full of water. The spectrophotometer will be attached to the cuvette, so collecting data can be relatively convenient. In order to ensure that no outside factors affect both the DNA-filled cuvette and the spectrophotometer, the remaining space will be filled with an opaque material surrounding the entire experiment. Due to COVID restrictions, the DNA experiment couldn't be tested properly since having access to the rocket wasn't possible at the time. Instead, more research was done in order to come up with an exceptional theory of the experiment if the experiment were to be physically tested. Now we have Lilia with the enzyme experiment.
The purpose of the enzyme experiment is to test whether rocket flight conditions have any effect on the reaction rate of catalase. An oxygen pressure sensor will measure the amount of oxygen produced from the reaction throughout the flight and will be compared to the data from the control experiment done under normal conditions. A 50 milliliter Falcon tube will be filled with 40 milliliters of hydrogen peroxide. The catalyst will be separated from the liquid using a parafilm, where upon launch it will break, releasing the liver into the liquid, starting the reaction. An optimal volume of substrate had to be calculated so that it would fit in the given space and that the reaction would last for the majority of the flight. Due to having a closed campus, we were not able to do any testing to validate our theoretical values.
Hi, my name is Justin Kissel. I'm the electrical lead, and Aaron Tiemens and myself will be going over the electrical system this year.
The electrical system consists of several main components. The foremost is the Telegps, which acts as our competition-approved GPS for locating the rocket. A Telegps is located in both the booster and the dart.
The next system is the flight computer, which takes in data from the DNA and enzyme experiment for storage, and it handles all the calculations for our Airbrake system. This system consists of a motherboard for connections, a power board, a radio board for transmitting wireless data as well as video from the onboard cameras, a data storage board for the experiment, and a data processing system for the Airbrakes. The last piece of the electrical puzzle is the Airbrake motor controller, which handles actuation of the Airbrakes using a stepper motor and receives instructions wirelessly from the flight computer.
My name is Alexander Burkhardt, and I am a part of the recovery sub-team. This is the recovery section. The recovery systems consist of 2 vehicles with 3 parachutes between them. Both vehicles have independent dual deployment altimeter systems. Each of these systems involve safety switches located in their respective avionics bays and black powder charges at each recovery event. The parachutes are completely designed and fabricated by MASA-Dearborn, made out of ripstop nylon and sewn together with Kevlar shroud lines.
Hi everyone, my name is Carson Easter. I'm part of the recovery sub-team. The booster uses RRC2 altimeters to signal both the drogue and main parachute deployments. These are located in the booster avionics bay.
Hello, I am Alexandra and I'm a member of the recovery sub-team. The booster drogue parachute is a cruciform shape and is housed inside of a radial motor located below the booster avionics. The booster main parachute is a circular shape and is housed inside of an axial recovery bay located above the booster avionics.
The use of 2 separate bays simplifies dual deployment by circumventing the need to retain the main parachute while the drogue is deployed on the same shock cord. Each parachute is retained to its own shock cord and eye bolt.
The dart uses RRC3 plus spurred altimeters to signal the separation of the dart from the booster as well as the dart's parachute. These are located in the dart avionics bay.
The dart is able to use one circular parachute by utilizing a reefing system. Upon its initial ejection, the parachute will inflate at its reef diameter and be retained by a single reefing line. At both ends of this line is a tender descender. Upon successfully signaling one of them, the parachute will inflate to its full diameter. Before that, it will have reached its first terminal velocity, achieved normally by a drogue parachute. When it's fully deployed, it will be able to reach its final terminal velocity before it collides with the ground.
Thank you for joining us for MASA-Dearborn's poster session. Please let us know if you have any questions.